Right, start recording. We are recording. All right. So this is nothing new. Okay, this is nothing new. We know the trend. It is going down a little bit. So the 2026 computer science job market for college graduates is challenging due to a downturn in entry-level hiring. Okay, so I know you guys are not graduating yet from with a four-year degree in 2026, but long-term demand remains strong in specific fields. Okay, um, so did I talk about the AI summit? I think I did talk about the AI summit on Monday. Okay, so that's information, right? That's one data point. So you might want to kind of talk to more people, find out, more data points. But there's one thing that is quite interesting for those of you who want to at least get an idea of what vibe coding is about, and at least give it a try, find out the limits of vibe coding and whatnot. You can do it with Gemini. You all have access of Gemini to Gemini already. The CCCCO, the California Community College Chancellor Office. Okay, so they already pay for 3 years of subscription. So as long as you're a student in a community college, you have access to it. So has anyone tried vibe coding? Nope. Okay, this is how you do it. You go to Gemini, you start a new chat, and all you need to do is to specify what kind of program you want it to write for you. Okay. For instance, I want to write an app, that is a counter. Okay. You know the Costco person at the door, they want to increment the counters. So you just say, I want to develop a web app that serves as a counter. I need one button to increment the counter, a reset button to reset the count to 0. Okay, let's just do that much, right? Oh yeah, it automatically figures it out. Oh, look at that, huh? Huh? And and you can what? HDL, like hardware description language. Just learn it yourself. Okay, so obviously you have not taken CISP 310 from me. You did. So HDL is like a script to put components into the circuit, and then you use your code to specify, which port connects to which other port. Programming is abstract. This whole field is abstract. Computer science, computer engineering, the whole thing is abstract. So you have to kind of so you might need to learn how to understand abstract concepts. There are techniques and strategies to do it. So that might be the first thing you need to do is to kind of look at some general strategies to understand. And we can use Gemini for that too. Okay, so now we can now say, okay, this is too simple. I need to have a list of the time when the increment button is clicked. Okay, so all you have to do is to say it, ask for it. It's like, okay, I also need a list of the date time of when the increment button is clicked. The reset button should also clear this list. Okay, and by the way, this is using the fast model, not even the thinking model. So now it's regenerating the code. Takes a little bit longer this time, but it will figure it out. Hmm. All right. So the code is all done. And now guess what? We have a list. So we click it and it locks the time. Click it again, lock, click, 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 and then reset clears the increment history too. So how are you feeling about this? What do you mean? Well, this is a standalone page. I mean, you can download this, put it into HTML document. Um, there are deployment environments that can do it. So Kiro.dev, and guess what? Guess what? They fixed the typo. Uh-huh. I didn't report it, but they fixed it. Somebody spotted it and go like, this is embarrassing. We need to fix the typo. I mean, if I have a typo in my OER, it is not as embarrassing, okay? Because I'm not a professional writer. And I don't have billions and billions of dollars behind me. So I do it for free. Jeez. So this kind of environment can actually help deploy your app. So it's a full cycle. Okay, you can use it to also manage your containers and the whole nine yard. So anyway, how are you feeling about vibe coding? Are you fascinated or are you scared? Does it instill fear? No? Why not? Hmm? What change it to non-react? Then you can say, I cannot use React. Do this in native JavaScript, and I don't even have to spell it. Okay, it knows what is React and what is JavaScript. See? Uh-huh. Look at that. Everything is now in native JavaScript. So this is not so much the future. You still need to know how to code, by the way. Okay. So the only thing that you need to, the difference, okay, I'm not sure whether I talked about this on Monday. So there are two main groups of people. One group would be dinosaurs like myself. I like to do everything myself on the command line using really primitive tools. Can I make something like this? Absolutely. Give me enough time, I can do it. Okay. And then the opposite camp would be people who look at computer science and go like, this is too hard for me. This is too abstract for me. I don't want to do this. So those people go to the vibe coding side completely. I'm not talking about you, by the way. So they go to the vibe coding side and they just go like, oh, I just need to prompt the AI to make the app for me. So there are these two extreme groups, but there are not enough people in the middle. So what do you mean by in the middle? The middle people can look at the code that is generated by AI, critique the code, find out what is wrong with it, okay? Because there are certain things that are too complicated to describe even using a prompt. Then you have to go into the generated code and fix it, okay? There are not enough people in that, in the middle part. They can do all the coding themselves, they have all the expertise to do it, but they can also know how to use AI to save time. Okay, so that is the key. Okay, it is debugger slash guide slash mentor. Okay, because when the code doesn't do what it's supposed to, can you properly describe what needs to be done and correct the code just by just using the prompt? So that is why this class and other programming classes come in handy because you are learning how to use a formal language to describe things. So is that okay? All right. And I think no, most of the four-year universities won't introduce you to vibe coding either. Okay. I think they're also in the camp of the dinosaur camp where they want you to write the code all by yourself. Okay. Which is okay. I mean, for education purposes, you definitely should write the code by yourself. But learning this on the side, learning what the tools can and cannot do. Okay, the most important part is what it cannot do, and I think that is really, really important. All right, so I'm just showcasing what you can do. There are a lot of little cool things that you can do with AI these days. And I'm gonna do one more thing. Okay, I'm gonna do one more thing just to illustrate what why AI can be really useful. So I can say I am having some challenges understanding abstract concepts in general in physics, calculus, and computer science topics. What is a good strategy to help me strengthen my skills to understand abstract abstract concepts? All right. Pretty general stuff, right? It's not very specific to a class, and it's a very common challenge in fields like this. It's a breakdown of effective strategies, visualize and connect, use analogies and metaphors in physics, calculus, computer science, blah 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 blah. So it gives people a strategy, a general kind of plan to understand more abstract concepts. So, yep, and you have access to it. You guys all have access to Gemini. I would say, give it a try. Find out what you can do. Find out what you cannot do. Okay, because you are not competing with AI, but you need to learn how to use it as a tool. So that is the key. Okay, don't look at it as a competition, but look at it as a tool. In order for you to make use of the tool, you have to understand how the tool works, right? And what kind of code it generates, and be able to understand that code. So that's going to be the challenge of your generation, is to kind of figure out where the boundaries are, what you can do, what you cannot do, what the AI can help you with, what it cannot help you with, and so on. So with that said, okay, we are moving back to the kind of technical stuff here. So what I have done, okay, this is something that you might want to kind of play with as well, is I made a spreadsheet. So I made this particular spreadsheet to have a series or sequence that is oscillating for one thing, and you can also see how the amplitude of the oscillation kind of converges to basically plus and minus one. So now you can use this to practice your understanding of the concepts that we have talked about. Okay, so the first thing you can do is to my my USB cable is not happy today. Um, now it's back, but the recording is still going. Okay, excellent. So your practice, or what you can do with this particular spreadsheet, is to practice all of these concepts. Okay, particularly you want to practice the limit of a sequence. So the question is, does this particular sequence have a limit? Okay, so how do we define the limit? My mouse pointer is right there. Okay, so what does it mean when I say for every epsilon that is a real number that is greater than zero, blah blah blah? Okay, so what is the blah blah blah? The blah 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 says there has to exist an m that is a natural number, so that for all other natural numbers that are great for all natural numbers, not all other, but all natural number j that are greater than or equal to m, the absolute value of k minus x of j, which is one particular item in the sequence, has to be less than epsilon. So how do you test that, right? So first of all, you need to set up some equations. Okay, so let's go ahead and set up some equations. So what I'm doing is I'm trying to make this as concrete as possible. Okay, I personally cannot think of anything as concrete as a spreadsheet, because you're looking at real numbers, you're looking at the formulae, and I think with a computer science background, the spreadsheet formulae should not be a problem. Okay, so that's what we're going to do. Okay, we'll find this, find the sequence. Um, so first of all, we have to set up as an epsilon. Okay, so we'll go ahead and set up an epsilon. So I go to the property. Personally like to do things like this, to use a particular sheet for all the constants. So now we go like, okay, this is our epsilon, EP epsilon, and just pick whatever value. Okay, so let's just say we pick 1.4 as our epsilon, which is greater than 0. It is okay to pick 1.4 as an epsilon. Then we go back to the sequence and then we ask that question. So now we go back and then we ask, we need k minus x of j to be less than epsilon, so we need to define k, which we suspect is the limit. So then we go back to the spreadsheet. Okay, what do you think is the limit here? If you have to guess that there is a limit, what do you think that's going to be? This is, by the way, 0, right? So you can see everything seems to be averaging to 0. So if it has a limit, I suspect it's going to be 0. Does that make sense? Okay, just because of the shape of this whole thing. So now you set up the limit, which we call k. So we go back to the property here. Okay, we go like, okay, we'll set up a3 as a cell as our k, and we suspect it is 0. Okay, so now we can name the cells, so it's easier to refer back to the cells. So we can go here, and then we go to data, and then we set up to have what is it? Is it Yeah, named ranges? Okay. So now we set up a new range. Okay, we call this exactly the same name, which is epsilon. Okay, there we go. Done. And then the next one we just call it k. Same thing. Okay, add a range. Okay, this is just k. All right. So in other words, I'm basically defining aliases, okay, to specific cells, so I can refer back to these values, without having to look at the row number, column number, and what is the sheet name, and so on and so forth. So now I go back here, okay. So the first thing I want to do is to perform that calculation, which is the absolute value, ABS, of whatever the number is minus what I think k is. Okay, so k is now quote unquote a variable that is tied to a particular cell. So that is okay because k is 0. That makes it very easy to compute. And I can make this a little bit more fancy too, but I don't want to waste the time to do it. Okay, so we can now see that, oh, okay, k is pretty easy. So now we have to compare the difference to our epsilon, okay? Because according to this, we are done with this absolute value. Now we have to see whether it is less than epsilon or not. So now we go back to the spreadsheet and then we ask that question, okay? We are basically asking equal, is this number less than epsilon? And we just spell out the word epsilon because I defined the constant, well, not constant, the named range earlier. So now we can go like, okay, is it the other way around? It should be epsilon has to be greater than, okay. So that's not, oh, that's fine. Okay, we just have to find out when it becomes true because in this case, the one that I have chosen will become true at some point. So we can see it does become true at some point. So it looks like, if the epsilon is 1.4, then everything is okay. So now it's time to kind of make it smaller. So the idea is if you look at the qualification here, if you make the epsilon smaller and smaller, then you are moving m further down the road. Okay, because the um, okay, let me show you graphically what we are talking about. And we look at this diagram, and let's close that. Okay, so you can basically see how, it seems like, everything is converging. So when you make epsilon smaller, so what is epsilon? Epsilon is basically defining a range of, a bound, so to speak. And we want, basically after a certain point, we want every single point to be within that bound. That is what epsilon is trying to do. So initially, if we have a large epsilon, then we can start early. But as you move, if you as you make your epsilon smaller and smaller, the starting index is going to move in that direction. Does that make sense? Okay. So 1.4, with 1.4, the sequence starts to become true, or we start to get into range at about 51. So if you look at this diagram, it's about here. Is that okay? So if I make epsilon smaller, okay, so let's say we just turn it to 1.3, okay, then just using this spreadsheet here, we can now see that it was right here, and now we have to move a little bit further down the list until we get to what 68. So when you go to the graph, 68 is going to be about here. Is that making any sense? So the question is, if I make epsilon smaller and smaller, as long as it is greater than zero, can I still find an m somewhere down the road where every single point after that is within epsilon away from the limit, which I suspect is a zero in this case. Okay, if there's a limit, it's going to be zero. So the answer to this question is because there's an oscillating component here that does not reduce magnitude over time. So that means if I make epsilon, something like zero point 0.9, then nothing is going to fit anymore. So when you make so you can see down the road here, everything is false. Okay, and it has to do with how I set up this little equation here. I make sure that it will oscillate over time. So that means if column D is all false, that means there is no limit. Are we good so far? That there's no limit in this case. The limit does not exist because the quantified expression here is false. I cannot guarantee this condition for every epsilon that is greater than zero. Now, can I make this true for certain epsilon values? Yes. But because this is a universal quantifier, that means this whatever part that is in the parentheses, that has to be true regardless of which positive epsilon I choose. If I choose 0.0001, I should still be able to find an m like this. But in this case, in this particular example, I specifically make it so that it is not possible. Is that okay? So this is why this particular function or this particular sequence has no limit because of the non-decreasing amplitude of oscillation. So now we can move on to some other concepts that we have talked about. So we now move on to limit superior. So lim sup or limit superior is finding the the minimum of maximums. Okay, because supremum is finding the maximum. So this k is essentially the outer loop determines the n, the inner loop determines the k. So this is basically finding all the maximum after a certain point of n. Okay, so let's go ahead and start with the inner portion first. We are trying to find the maximum of x of k, past a certain point, whatever n is supposed to be. So the equation to do that is a little bit complicated, but I can just kind of, specify this. Okay, so we are looking at. I'm using a uh, array formula, which is kind of a more advanced concept in spreadsheets, but it's not super duper complicated. So array formula allow you to specify a format for a bunch of cells all at the same time. So I don't need to specify a cell at a time. So what we need to do is to find out what is the maximum. Okay, so maximum takes a range of cells too, but because the range depends on okay, I'll just use an example for sequence 9. Okay, for x9, it means from this point on I need to find the maximum. For 14, it means from this point on, I need to find the maximum. Are we getting the idea of we are trying to find maximum based on which row we are starting with? And then it goes all the way to the end. Are we understanding that concept? Okay. Okay, so the way to do this is to use a concept called offset, which allows you to programmatically specify, where is the starting point and where's the ending point of that. So the starting point is going to be um, this particular cell over here. Okay, so we are looking at this cell, which is the original value. So column B is xj. Okay, that's your x value, which is the value of the sequence. And then comma 0, 0. Let's see. Yeah, 0, 0 is fine because we are not offsetting in any way. And the next number specifies, so how many do we want, down the list? So I have a kind of little clean shorthand to do this. It is called series length. Okay, so series length is the entire series all the way down. And I have to subtract the current row number to get to the length of the entire thing. So it's row number, and then we have to add one back to it. So this specifies from B1, how many cells are we considering? In this case, we are emulating infinity using series length because this is a limited length series. So I'm just using this as an equation. And then the last number here is how many columns do we want as the width of the entire thing. And we just need one, okay? So I think this should do it, okay? Apparently not. Okay, so what am I missing here? The maximum of offset B1. Okay. Mm, I actually tried that earlier and it seemed to work. Well, if this is not working, we can always, go back to the replicate, formula method. It'll still work. It's just kind of, it's not elegant as a solution. All right, well, it's still working okay, except this one is off by a little bit. I think they're off by hmm, that's interesting. It's skipping every other. All right, so let me try to debug this. Okay, series length minus row number plus one, and we want this to be a column of one. That is strange. So starting with B1, this one starts with B2. Oh, I know why. Because this is a negative 6.25, so negative 6.25 is a negative value. So if I start at row 2, the maximum is indeed the 5.20. So that's why it looks like it is just skipping a number. That's because we have positive, negative, positive, negative, positive, negative. So that's why it looks like this. So these are these individual items in column E. Each one is a supremum. So now what we need to do is to take the infimum of all the supremum. So in other words, what we are trying to do is to take the entire column E, and then we look for the minimum of the entire column E. Is that okay? So to do that, I'm going to go back to a property, because otherwise it's a little bit kind of difficult to read. So I'm just going to do it over here. We'll just say the overall infimum is the minimum of in sheet one, and that would be column what? Column E, and we'll specify column E, exclamation point, column E, E. Not sure whether that's going to work. That was a problem. Oh, because of the extra parent. There we go. Overall infimum. I think I'm off. It should not be negative. Yeah, it should not be negative. Why is it negative? Okay, maybe we should specify E1 all the way to really just the end of the whole thing. So 5, 3, 1, 5, 3. 153. All right. So that's the overall infimum. So that means this whole thing, this is our limit superior. This is how we calculate the limit superior, lim sup. So are we doing okay so far with understanding how lim sup of the entire series or sequence is calculated? Okay, we got some nods. Okay, now this spreadsheet is available to you. Okay, we can see that there is a, what is that supposed to be? Looks like a Pokemon to me. Anonymous dragon. That doesn't look like a dragon. The dragon has wings at least. Hmm. Anyway, this is limit superior. What do you think is limit inferior? Kind of the opposite, right? Okay, so we'll work on it. Okay, we'll work on limit in inferior. So limit inferior is basically taking a whole bunch of minimums and then we try to find the maximum of the minimums. Kind of the same deal in terms of structure, except everything is opposite. So we go back to sheet one. If this is how we find the maximum, we just have to kind of copy this. Okay, we copy this entire thing and stash it over here. And instead of saying maximum, we say minimum. There we go. And then we just have to extend this all the way down. Come on, comma. Oh, I have to click on this one first. There we go. So now we have, basically each number here, like I'll pick a number like this one. So this one is basically the minimum starting with x11, and then it's the minimum of x11, x12, x13, x14, all the way to supposedly infinity. But since this is an actual spreadsheet, there's a certain limit to it. Are we good so far? Okay. So now we go back to here and then we try to calculate limit inferior, which is the overall um, superior, the overall inferior. Uh, this is the sup. This is the sup. This is the supremum of all the infimums. And the way we calculate that is basically the same thing that we do here. And then you just copy the whole equation. And now we are trying to find the maximum of the minimums. There we go. And that doesn't make sense. Oh, because it's not E, it should be F. There we go. This is F, and this is F2. There we go. Now it makes sense. So are we doing okay so far? In other words, what we are really asking is the function itself is going to oscillate to no end. Okay, so there's no actual limit. But when you look at the shape, it is still there's an envelope. Okay, so the limit superior and limit inferior is basically saying at some point in time, okay, we should be able to define an upper bound to cover everything past that point. That's limit superior. Limit inferior is basically saying, okay, at some point in time, we should be able to define, a lower bound that covers everything. So that's limit inferior and limit superior. They are basically trying to define the envelope, which is the um, upper bound and the lower bound as the sequence goes to infinity. Are we understanding those two concepts? Okay. So in this particular case, okay, given all the data points that we have, the answer is okay. Limit superior is 1.14. Limit inferior is negative 1.13. So those are the definition of the terms when implemented using a spreadsheet. So are we doing okay so far? Okay. Are there any questions about the spreadsheet formula that you want to ask? No questions? Okay. So the other thing you can do is to replicate exactly what I'm showing in the spreadsheet using a C program. Okay, you can basically just say that, okay, we are not going to have an infinite sequence, we have a finite sequence, and then just try to find the limit superior within that sequence using C code. and then try to find the limit inferior and, well, I cannot remember which one I said already. So limit inferior and limit superior. Use C code to do the same thing. Because as soon as you write the C code to get to the same result, you understand, from the programmatic perspective, from the coding perspective, using a loop, what you need to do to accomplish exactly the same thing. So, so that's one way for you to get a better understanding of, these concepts. So this really kind of goes back to the question that I asked, Gemini, how do I understand more, abstract concepts? You map it to things that you already know. Okay. And I know you guys know how to set up loops because CISP 360 is a prerequisite to this class. Are we good so far? All right, cool. So now we have the terminology to define what is an upper bound. So upper bound is that you have two functions. One is f of n, the other one is g of n. F of n is something that we don't want to know because it is complicated. Okay, there are a lot of coefficients to figure out. There are a lot of components that we have to figure out. We don't want to really know what is f of n. The g of n, on the other hand, is something that is really easy for you to understand. You can have g of n being 1, which is a constant time. You can have g of n being n itself, which means you have a linear time. You can have g of n to be n squared, so that means you have something that is proportional to n squared. So g of n is typically something that's really easy to figure out. F of n is the ugly one that you don't want to figure out. Okay. So now the question is, how do we relate f of n to g of n? Okay, whether it is a something of the other one or not. So the definition of g of n being an upper bound of f of n is defined as follows. Okay, and you can see that we are using the little element of symbol here. So that means the function f is really just an element of the big Omicron notation. So what we normally call big O, that so-called O is actually Omicron, uppercase Omicron, which is essentially O. So you can also see, how, big O of G of n can have many, many elements. F of n is just one of them. So the question is, how do we know whether f of n, which is a really ugly form, is a really ugly function with a lot of coefficients, a lot of components, whether it is an element of big O of G of n is determined by whether the lim sup of f of n divided by g of n, and you take the absolute value of that, whether it is less than infinity. Essentially, what you're really asking is does this resolve to a particular number as a real number? If it does resolve to a particular number that is a real number as n approaches infinity, then we can now claim that f of n is an element of big omicron, otherwise known as big O of g of n. Is that okay? So here's a test, okay? Let me see if you guys understand, what I'm talking about here. So think about bubble sort, okay? We know bubble sort is not the quickest, sorting algorithm. It has a time complexity of n squared. Very good, okay? So we kind of know that f of n is proportional to n squared. So now the question is, if I make g of n, say, n cubed, okay, would is is the time complexity of a bubble sort algorithm an element of big O of n cubed? That is the question. All right, so let's try to figure out mathematically, what this means. I know you guys have taken at least a pre-calc. Most of you probably have finished, a few calculus classes already. So we know that f of n, okay, is n squared sum k1 times n squared plus blah, 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 blah. But none of the other terms is going to grow as quickly as n squared, okay? So that we know that, right? So I now define g of n to be just n cubed without even any constant. Are we doing okay? So now I look at the division, okay, f of n divided by g of n. So that means we have k1 times n squared plus some other terms that grow relatively slowly compared to n squared. And then the whole thing divided by n cubed because that's how g of n is defined, okay? So now the question is, as n approaches infinity, what happens to this particular formula expression? What do you think? Does it become k, or does it become something that is even better than k? What does it become? Hmm? Zero, that is correct. Okay, it becomes zero because k is a constant. Okay, which means it is a particular number. At some point, n is going to match k, and then after that point, n is going to be greater than the k. So that means this whole thing is going to become zero. So now the question that you have to ask yourself is zero less than infinity? Yes. So that means you can actually say that bubble sort is a big O of n cubed algorithm because it is it's an upper bound. Okay, it doesn't have to be a tight bound. It is just an upper bound. Is that okay? So when people use the big O notation, most of the time they don't know what big omicron actually means. Are we good so far? So this means in the final exam, I can kind of give you guys questions like this kind. Okay, this is an algorithm. Does it belong to this big omicron set, and so on? I mean, this one is pretty clear. All right, so the next one is something that we just looked at. Okay, it is basically looking at the same division, the same ratio, and ask, does it become zero? So in this case, it does become zero. So when it does become zero, what does it mean? It means f of n is an element of little o, or lowercase omicron of g of n. Most people do not bother to specify this because little o, or little the lowercase omicron, means negligible, which basically says this g is not really useful. It's a gross overestimate of f of n. So when we say that g of n, when we say that it is when we use the little o notation, it means g of n is a gross overestimate of f of n. So that means you can always claim, okay, any sorting algorithm, like bubble sort, selection sort, um, merge sort, quick sort, and so on, they are all big O of n squared. You can actually claim that because n squared is simply an upper bound of the actual time complexity. Now, how upper bound is it? Well, it can be grossly overestimating, and it still counts as big O. Are we doing okay so far with this concept? All right. So once we have upper bound, we also want to take a look at lower bound. So lower bound looks almost exactly the same, except what we're comparing to and which we were comparing to. So lower bound simply says the ratio between f of n and g of n has to be greater than 0. How much greater than 0? Doesn't matter. Okay? So that means, as long as f of n divided by g of n, when you look at the absolute value, as long as it is greater than 0, then we have found the omega, which is the lower bound of the complexity. Are we doing okay so far? Okay. So, for instance, you can claim that mm, constant time, okay, is a lower bound of any sorting algorithm. Okay, because constant time means it is a one, is a single constant. So when when g of n is just one, and f of n is n squared or n log n, then this whole thing is going to be it's going to approach infinity, which is greater than zero. Okay, which leads us to dominant. Okay, so dominant is the opposite of negligible. It is basically saying g of n is a gross underestimate of f of n. So that means when you take the limit, it is approaching infinity. So this is how we say f of n, g of n, sorry. This is how we say g of n is a gross underestimate of f of n. And the symbol to use here is lowercase omega. So big omega is just saying it's lower bound. Little omega says it is a gross underestimate. Are we good so far? Because we have four different bounds we talked about up to this point. Omicron has to do with upper bound. Uppercase is just saying it is an upper bound. Lowercase means it is a gross overestimate. Omega means it is lower bound. Uppercase means it is just a lower bound. And when we use lowercase omega, it means it is a gross underestimate. Are we good so far? There are four concepts right now, and I just want to make sure that you guys are getting all four concepts. Okay. So now we have type bound, which is ideally speaking, we want to find the type bound, which is denoted by big theta. So we say that f of n is an element of big theta of g of n if and only if f of n is an element of big omicron of g of n, and f of n is also an element of big omega of g of n. So the same function serves both as the upper bound and also the lower bound. That is when we say, oh, this is gold, man. This is what we want. Because finally, we have found a reasonable estimate of f of n that is going to basically everything approach a certain constant that is non-zero. The ratio itself approaches a constant that is non-zero because we just need to know how fast something is growing. We don't really care that much about the constant itself. So are we still doing okay so far with the five different kinds of bound? Upper bound, just upper bound, but overestimating. Lower bound, lower bound that is way under or over underestimating. And then we have tight bound. So those are the five different ways to describe how the time complexity or space complexity of an algorithm relate to a simple function such as n squared, log of n times log of n, and so on. Are we good so far? Okay, all right. So that is, basically all the notations. Um, if there are no questions about these notations, we can move on to the next topic. So do we need more time to think about whether we have questions about this particular module? No questions? All right. Are we starting to be more comfortable with the mathematical notations or the concepts thereof? You doing okay? All right. All right, so if there are no questions, I want to move on. I want to skip a few topics to get to graph algorithms. And then when we have time, we can come back to some of the other topics because graph algorithms is actually kind of important. So this is the module for graphs. All right, so we're going to define what is a graph. So a graph is a two-tuple, which means there are two components. Can anyone remember, in propositional calculus, how many components are there in order to define a propositional system? Yep, four. There are exactly four. The four are alpha, which defines the symbols. We have omega, which defines the operators. They call those connectives, but it's basically operators. The third one is iota, which are all the well-formed formulae. For some reason, it's known to be true. Okay, and then the fourth one would be the transformations, which we know as zeta. Okay, so in the case of a graph, we only have two components. One is the set of vertices, and the other one would be the set of edges. So we're going to take a look at what what does it mean? So edges from E must be led from one vertex to the next vertex, and the path is defined to be something like this. So we're going to take a look at what a path means in this case. All right, so we are saying for every integer I, for every natural number, for every natural number I, if I is less than or equal to the number of items in a path minus 2, okay, so it has to be minus 2, not minus 1, and we are numbering things with 0 orientation. So we are now saying, okay, if you compare element I of path P to, okay, you make a tuple out of element I of P versus element I plus 1 of P. This particular edge, this two tuple, has to be an element of E. So before we go any further, I think it might be helpful to kind of take a little bit step back to the more kind of fundamental items of related to a graph. A graph is a two-tuple, V is a set of vertices, and E is a set of edges. There is no limitation as to what V can be. You can use alphabets, okay, A, B, C, D, E. You can use numbers, 1, 2, 3, 4, 5. It doesn't matter what the elements of V looks like, okay? The limitation is more on E and not so much on V. So E has to be a subset of the Cartesian product between V and V. And most of you remember something that looks like this as relations, okay? And also functions, because a function has to be a subset of the Cartesian product between the domain and the codomain. A relation has to be a subset of the Cartesian product between the set and itself, okay, whatever set that you want to define the relation over. So in this case, it is kind of like that, okay? So the set of edges has to be a subset of, the Cartesian product between the vertices, the set of vertices and itself. So this means each edge is a two-tuple where the first item, we call the first item the tail, and the second item we call the head are both elements of V. All right, so I think some examples would be helpful. Yes? Okay, so let's go ahead and take a look at some examples. And I'm going to put it on the whiteboard. Okay, where's the eraser? Eraser's right here. There we go. Just because it is easier to visualize when I'm using the whiteboard for stuff like this. So what is a graph? A graph is, okay, think about Google Maps. Okay, think about Google Maps in the context of certain parts of San Francisco. Why do I pick San Francisco? Because in San Francisco, some streets are only one way. Okay, so now we go like, okay, so we have your vertex A going to vertex B. So all the vertices are representing intersections where you have a choice of, okay, I can go this way or I can go the other way. Okay, and we'll just say that vertex B goes to vertex C, and then vertex C goes to vertex D. And to make this a little bit more fun, we'll just have another edge from vertex B to vertex D. So this is how we look at a graph from a visual perspective, okay? So now the question is, how do we represent the same graph using a set notation, standard? But before we move on, does everybody kind of get an intrinsic understanding of what this is representing? You can reach B from A, you can reach C from B, you can also reach D from B, and then you can reach D also from C. Are we doing okay so far? Okay. So in this case, the set of vertices is going to be just A, B, C, D. It is the set of all the intersections, okay? And also including the starting point and what looks like the destination. The set of E, I'll let you guys talk about it. Okay, what do you think are the elements of E, or the elements of what are the edges of this particular graph? Okay, say again? No. Well, I'm looking for very specific elements here. We know those have to be what? tuples, right? We know they have to be tuples. Okay, so we have AB. Okay, very good. And what else is in the set? BC. Okay. D, huh? BD. Yep, BD is correct. And then we have CD. That is correct. All right. So are we sure this E as a set is a subset of the Cartesian product of V versus V? Yep. And that's it. Okay. This is how we define it. So now the question is, why do we call the first item of the tuple the tail, and the second item is called the head? Okay, so we'll pick one of them. Okay, we'll just pick CD. So in the tuple CD, C is known as the tail, and then D is known as the head. How does that make sense? Because they are parts of an arrow. That's why. Okay. So are we understanding the terminology? What is the tail? What is the head of a two-tuple as an edge in a graph? Okay, we good? All right. So once we understand those basic terms, then we look at the other terms, which is a path in this case. So a path is by itself a tuple, but how many items in a tuple kind of depends on the path, the length of the path. So in this case, a path is A, B, C, D is a path. A, B, D is also a path. Okay, so we'll take a look at A, B, D. A, B, D. So I claim that this is a path because it satisfies the requirement of whatever I specify over here. Wherever the mouse pointer is pointing to. So we now ask the question, are we really sure that it meets this requirement? So the outer quantifier is basically saying I just has to be a natural number. But bigger we have a restriction here that says I has to be the length of P, the number of items in P, minus 2. Okay, so that means um, we have 0 and 1 in this case. Does that make sense? Because the length of the path here is 3. So 3 minus 2 is a 1. So how many natural numbers are less than or equal to 1? Let me ask that question one more time. How many natural numbers are less than or equal to 1? 0 and 1. So there are 2, right? Okay. So now we say, okay, I can be a 0, I can be a 1. Okay. So when I equals to a 0, I am looking at element 0 of the tuple and element 1 of the tuple, and I'm asking if I make turn that into a two tuple, is that in E? In other words, in this case, I'm asking whether AB is in E or not. What is the answer? Okay, this is yes. So now we look at the case when I equals to 1. When I equals to 1, we are looking at element 1, element 2, turn it into a two tuple, and ask whether that two tuple is in E or not. So we are focusing on BD. So we ask, okay, is that in E? Yep. Okay. Since we only have to iterate I from 0 to 1, in both cases they are true. So that means the entire quantified expression is also true. So that's the reason why we have this implication or the left-hand side of the implication, because some people is going to say, but what about 16? 16 I equals to 16 because 16 is a natural number, right? Then you ask the question, is 16 less than or equal to the number of items in the path minus 2? No. What happens to the implication when the left-hand side of the implication is false? Yes. The implication itself is true. So that means, oh, so that means we are really just focusing on the two cases when I equals to 0 and when I equals to 1, because as soon as I is at least 2, the left-hand side of the implication becomes false. And the implication becomes true, which means, oh, okay, they are not going to hurt the universally quantified expression. It's not, nothing is going to be false after that point. Is that okay? Okay, so when you look at this side of the implication, if I is at least 2, then this particular part, this comparison is going to return false. Yeah, bar p bar, which is the size or the length of p, is 3. Yep. Okay, so okay, I'll ask you this question. What happens when I equals to 16? Okay, evaluate that for me. 16 is less than or equal to bar p bar minus 2, and we know this is 1, right? So we are really asking, is 16 less than or equal to 1? The answer is no. And how does that change how does it affect the implication? Exactly. So everything, okay, as when I is at least 2, which means 2, 3, 4, 5, all the way, they all make the implication true. So the only thing that can make the implication false is when I equals to 0 and when I equals to 1. Yeah, then you have to consider more. Yep, yep. So in addition to that, I just use English to express that a path cannot contain duplicates of a vertex. So you cannot repeat a vertex because the graph itself may contain a loop, okay? So I can say, okay, maybe I can have a loop here because, oh, there's an edge going from here to here. It becomes a loop. But even if it was a loop, okay, and it satisfied this requirement, the path A, B, C, D, A, or I should say the tuple A, B, C, D, A is not a path because vertex A is duplicate, is a duplicate. A path, by definition, by this mathematical definition, cannot have duplicate vertices. Oh, okay, without overlapping, without crossing. Yep, yep. So are we okay with the term path? Okay. Well, let me give you another example, and you guys tell me whether it is a path or not. Okay. So let me erase this one, erase this part over here, and we are going to consider A, B, oh, B is okay. So we'll do it the other way. We'll do a C, D. So we're including the red edge over here. So we're considering DA. We're considering DA as a part of the graph at this point. So we'll go like this. Okay, is that a path? How do we evaluate whether it's a path or not? Okay, I equals to 0, I equals 1. When I equals to 0, we are asking, is CD an element of the set of edges? We now have 5 edges here. So you go like, oh, okay, CD is right here. It is one of the elements. Check. When I equals 1, we are looking at DB. So now we're asking, is DB an element of E? You go like, nope. Okay, not the case, right? But because the quantifier is a universal quantifier here, so that means if you can find one case, okay, if you can find me one value of I where this expression is false, then it is not a path. So that means the tuple, the 3 tuple of CDB is not a path. So I'll be okay so far with evaluating whether a tuple of vertices is a path or not. That is correct. It's a directional graph. Yep. Oh, of course not. This is just an example. Yep. All right. So I think we are starting to get all the basic ideas. Okay. So let me ask you this question. What about this as a path? Is it a path? This tuple with only one item in it, is it a path? So before you guys go like, okay, a path implies that there should be more than one vertices and whatnot, don't do that. Okay? Use the definition. Plug everything into the definition. So in this case, the definition is, okay, what is bar p bar in this case? I only have one single element inside the tuple. So bar p bar, which is the length of p, is going to be 1. What is 1 minus 2? -1. Do we have any natural number that is less than or equal to -1? No. So that means what that means the left-hand side of the implication has to be false for every I possible. So what does it mean for the universal quantifier? Has to be true. So that means this is a path by definition. So go with the definition. Okay. Do not try to understand something intuitively, because sometimes when we think about things intuitively, then we go like, oh, it doesn't make sense. Okay, because a path is supposed to have some length to it. Nope, does not. Which also means an empty path is also by definition a path. Okay, when you have a tuple that has nothing in it, that means the length is a 0. So that means p bar minus 2 is going to be -2. Do we have any natural number that is less than or equal to -2? No. So that means the implication is automatically true, which also means the quantified expression is also going to be true, because it doesn't matter which I you choose, the implication is guaranteed to be true. So that is how we basically fall back to definitions and think about it by substituting I with specific value. So that way it becomes concrete. So this is me helping you to come up with a strategy to understand abstract concepts. Plug in specific numbers. Turn the mathematical notation into a loop, because you already know how to work a loop. Question? So if you want to use a definition like the mathematical notation for detecting duplicates, there are okay. So let's see how we can um, let's see how we can use a quantified expression to express no duplicates. I think this one does not guarantee no duplicates, because with this expression in our current example graph with the red arrow, A, B, C, D, A is a path. A, B, C, D, A, would satisfy the unit would satisfy this requirement, but it won't satisfy the other requirement because we have a duplicate. Okay. Yes. Yeah. Furthermore, which means and, right? Okay, so we're now we okay, this is I think this is a really great opportunity, because now I know what I want to express, which is a path cannot contain duplicates in of a vertex, duplicates of vertices. So now the question is, how do we use mathematical notation to express that? And this relates all the way back to the AI discussion, because how do you specify the requirements of your program or whatever you want to make to the AI so that it understands the constraints. Okay. Now you can use something like this. Okay. A path cannot contain duplicates of a vertex. You can use that. But that is now you're at the mercy of the AI understanding natural language and understand the word duplicate the same way that you do. All right. So the best way to do it is to use mathematical notation because it is absolute. So now the question is, how do we use mathematical notation to do this? Is it okay for me to erase a part of this on the whiteboard? Okay. So I'm just going to erase this part here. Okay. All right. So let's think about how do we detect duplicates. So let's just say that we want to say, okay, this expression detects duplicates. So if you want to detect duplicates, then we can say there exist two non-equal natural numbers. Okay, we'll just call those x and y. Okay, so there exists x, y, and they are both in a natural number. Okay, what do we want about these two? Well, the first thing is we want both of these to be a valid index into the path. Okay, so that means they're both greater than or equal to 0. I don't have to state that. Why don't I have to state the lower bound of x and y? Because they're already natural numbers. Okay, natural numbers start from 0. So I only have to define an upper bound. So now I can say, as I need x to be less than bar p bar, and we need y to be less than bar p bar, so that they become valid indexes into the path. Is that okay? We also want x and y to be different. Okay, so we now specify, okay, they have to be different, so x does not equal to y. And then one more thing, the last one is going to seal the deal, okay? Because we can now say, oh, if you look at element x of the tuple, if it is the same as element y of the tuple, then we just found a pair of duplicates within the path. So this expression here is confirming that they are duplicates. So if you want to say we don't want duplicates, just put a negation. Are we, is that making sense? So this is me in real time, you're converting a concept that is written or specified as an English statement to the mathematical notation. Because once you have the mathematical notation, turning that into code is a snap. Because in JavaScript, um, there are two methods, two vectors or arrays or lists. One is called sum, which is existential quantifier, and then the other one is every, which is the universal quantifier. So we can map these mathematical notation to JavaScript code like one to one. Once you figure out the mathematical notation or the structure of the expression, you can convert that to code. It's one-to-one correspondence, which is great. So this is one of the reasons why I kind of push this kind of notation in this class, because it is language independent. You can have JavaScript, you can have Python. Python has exactly the same methods in a vector or a list. I think Java itself probably has similar features. So that is the reason, okay, why I push for mathematical notation, because it is just an abstract way to capture a concept that is closely related to actual coding. Looks like you have a question. Mm, I'm not sure. I cannot visualize, the equation or the formula that you're telling me. So P is not a set. It is a tuple. It is a tuple, so you cannot use the element of, to specify whether something is in the path or not, because it can occur multiple times. Yep, yep. So, but this can do it because it's looking for, it's enforcing. Okay, let's look at the why we have these expressions in the conjunction. The first two items in the conjunction, make sure that x and y are in range so that they are valid indexes into the path. This one guarantees that x and y are not the same because the same vertex at the same position, of course, it's going to be the same itself, right? So this guarantees that we are looking at two different items within the tuple. And then the last one says, oh, they are they're different items in a tuple, but yet they are the same. So that means we have a duplicate. All right. But this has to do with what I talked about a little bit earlier with the AI, vibe coding thing. Because if you can use mathematical notation to specify the constraints when you enter, the prompt, okay, I'm not sure whether I still have it or not. Nope, I don't have it anymore. When you use mathematical notation to specify the constraints, there's no ambiguation because it's a mathematical notation. Just like, in programming code, there's no two way of interpreting the same expression or the same, statement. All right, so we are almost running out of time, but I can at least outline what we'll be doing in the following week. So next week we will use one day to talk about Dijkstra's algorithm, and then we'll use the other day to talk about the A star algorithm. So it would be very helpful for you to at least have a glance over the actual algorithm itself, okay? And make sure that you understand, the at least the individual things that we have to do, not so much together what it does, but the individual statements. And these are both specified in pseudocode. I guess you can call that the Python-ish, pseudocode because indentation, indicates nesting. But other than that, I think you guys can read it. Okay, it is not actual code; it is pseudocode, but it makes use of things that you already know, like loops and conditional statements and so on. So try to read that over the weekend, and then next Monday and next Wednesday, we'll go over the algorithm. I will trace the algorithm. Okay, we'll go through the algorithm step by step, use a spreadsheet to kind of indicate the state of the entire program at various stages. All right. And yes, we do have class next Wednesday. For people who think, man, do we have class on Wednesday? Yes, because it is one day before Thanksgiving. It is not Thanksgiving. And if you think you have other things that you need to do to prepare for Thanksgiving, well, I mean, you can allocate time otherwise, okay? Because that is not a holiday. So I will teach on Wednesday. Because I know some professors just cancel classes for the entire week. I cannot do that. We have too many topics that we still have to go over, so we cannot really miss a single class. All right. So I will see all of you next Wednesday, Monday. I'll see you next Monday and have a nice weekend.